Today we're going to be looking at lengths of segments within circles. So we looked at a similar situation yesterday with the angles formed by two chords intersecting in a circle. Now we're looking at the lengths of those chords, or lengths of parts of the chords. So this first theorem says that Cx, the length of Cx, times the length of Cy will equal the length of BC times the length of AC. So that's an interesting relationship, and here I'll show you in Sketchpad what that looks like. So here I have two chords intersecting in the circle. AB is 2.11, AC is 5. So you multiply those and you see a product of about 10.55. It's pretty close. It's probably due to rounding because it's measuring the actual length of these segments. AD 2.89, AE 3.65. Multiply them, you get the same product. So as I move it around, the product of those segments always stays the same. No matter where it moves, no matter where I put point A in the circle, you can see that these two products of those chords are always the same. Kind of interesting. So why don't you pause the video here and give these two problems a try. This is a pretty standard problem on the quiz and the test. Obviously 3 times 8 is going to equal 6 times x, so x is going to be 4 in this case. Over here in problem number 2, 10 times x is going to equal 6 times 12, so x comes out to be 7.2. This one is just a bit more challenging. You remember that ED would have to be 4 because this diameter is perpendicular to this chord, and so because it is perpendicular to the chord, it also bisects the chord. So that would have to be 4. Now we have two chords intersecting. Diameter is a chord. So we could find what x is by using our little relationship here. 4 times 4 equals 2 times x. X comes out to be 8, but they wanted the diameter AB, so that's going to be 8 plus 2. So here's a cool little challenge problem for you. See if you can figure this one out. Well, you see two chords intersecting here. Here's a chord and here's a chord. So I could find the area of this square if I could find what x is, what the side of that square is. So let's see if I can find the lengths of these other segments. If this area is 16, then that would have to be 4. The side of the square would have to be 4. The side of this square would have to be 5, square root of 25. And then this one would have to be 10. So now I can see I have 4 parts of two chords. So 5 times x would have to equal 4 times 10. X comes out to be 8. So the side of the square is 8. That makes the area of the square 64. So just a little review of everything we've talked about in the last 2 days. These are all the angle relationships up here. I just talked about this one regarding segments, that the product of the segments of two chords are going to be equal to each other. Next I'm going to talk about the segments on the outside of the circle. You know, how if the point of intersection of two sequences outside the circle, how these segments relate to each other. And then this one below is very similar to this one. So this is called the external secant to secant product theorem. So in other words, if I have two secants that intersect each other externally outside the circle, then this is going to be my relationship. The external piece times the whole secant is going to be equal to the other external piece times the whole secant. In other words, AB times this whole thing, AC, is going to be equal to AD times AE. The biggest mistake students make with this is they take AB and they multiply it by BC instead of AC. But it's the whole thing. Okay, so let's take a look at this in Sketchpad. So I'm going to start by reviewing the when the point of intersection is inside. The product of AB, which is this segment, and AC, which is this one, multiplies to 11.04. and then AD and AE multiply to the same thing. Now, as I move point A outside the circle, the relationship between AB and AC stays the same, but what happens is AC is this whole piece now. It's not just part of the segment, it's the whole segment. So the relationship's the same though. AB times AC is going to equal AD times AE. The formula hasn't changed whether it's internal or external. It's just when it's internal, it's the pieces, and when it's external, it's one piece times the whole thing. So kind of interesting little relationship there. So why don't you give this a try? It's not 5 times 8 equals 6 times n, if that's what you're thinking. That's what a lot of students do, and they mess it up. It's the external piece 5 times the whole thing, which would be 5 plus 8, or 13. And then it'll be 6, the external piece, times the whole thing, 6 plus n. And you distribute, solve it. You're going to come out with kind of a nasty fraction, 29 over 6, or 4 and 5/6. So this is the last formula on your list of formulas, and it's very similar to what we were just talking about. The external times the whole thing is equal to the external times the whole thing. It just so happens when it's a tangent like this, the external is the whole thing. So it becomes AD times AD, or AD squared. Let's take a look at this in Sketchpad and see what this looks like. So here I would have the situation with the external point. If I go ahead and move that external point so that it lies on the tangent, you see it's the external times the whole thing, 60.66, equals the external times the whole thing. So you end up squaring it. So it's really no different from the other one. It's just this point is moved down to be a tangent. And here's the last problem for today. See if you can find x. So we have external times whole thing. So 5 times 5 plus x is going to equal 10 times 10. We distribute, solve. Looks like x is going to be 15. And here's your mistake of the day. All right, have a good one. Talk to you soon.